All right. Well, hello, Physics C. Welcome to your first ever video lecture, even including from last year. I didn't even make videos going over Physics C stuff. So this is kind of exciting, right? All right. I'm going to start. So obviously, if you see like the bold underlined sections, I'm just going to do one video per section. Okay. And then, yeah, we'll just kind of follow like that. They're kind of structured a little bit differently than the Physics 1 notes. Okay, so voltage and electric current is the first section of this notes right here, circuit basics. Okay, electric charge, and it's kind of a lengthy definition, is a physical property. Okay, okay, of an object that causes it to be attracted or repelled from another charged object. Charged object. Okay, so objects may be attracted to one another or repelled from one another, and that's kind of the responsibility of electric charge. The symbol is typically a capital Q. Okay, and the units for charge is what we call a coulomb. Okay, and that's shorthand with a C. Okay, a coulomb. Okay. You're gonna a lot of times hear people use the word coulomb interchangeably for charge. They'll say coulombs of charge. It's a unit of charge. Okay. Elementary charge is on your equation sheet. It's a constant. Okay. You don't have to memorize it, but if you want to save time, you can. This is the charge on one electron slash proton. Okay, is the charge on one electron slash proton. And the value of the elementary charge is denoted by a lowercase e, and it is 1.6 times 10 to the negative 19 coulombs. Okay, so that's the charge that one electron, that's the charge on a single electron or a proton. Okay. Electric current is very similar to maybe something like a river current or water flow, right? This is the motion of electric charges. Okay, so the current is like the flow of the charges. Okay, we're going to look at two different types in this class. This is kind of a broad overview. Okay, DC and AC. Okay, direct current and alternating current. DC is direct current, and that means that charges move in the same direction. Okay, with constant velocity. Okay, AC means the charges oscillate. Okay, so if you were to graph current versus time for either case, this is we'll draw the AC one right now. Okay, this is time, this is current. Current is denoted with an I. Okay, if you were to draw current versus time for an alternating current, it would look like this. It would fluctuate. Right? Okay, and if you do it for DC, it's not going to be very special. Okay, it's just going to look IT. It's just going to be a flat line. Okay, because the current stays the same. It's constant. It's not changing. Okay. There's two types of current, a conventional and electron. Okay. In this class, we pretty much just look at conventional, but you do need to know what they are, or at least for this unit, we just look at conventional, right? Conventional current, okay, is that we pretend that the positive charges, which I tried to color code as blue, I have a better blue pen over here. Okay. We pretend that the positive charges, okay, move from the positive terminal or an area of positive charge to an area of negative charge, okay? So we pretend that positive charges move from the positive terminal or the positive area to the negative. However, that's actually not the truth. The truth is the electron current is the truth. Okay? Electron current is the truth that electrons, okay, move from the negative terminal or the negative area of charge to the positive. So it's actually the other way around, right? Okay. When we look at circuits in this class, we pretty much always go with conventional current. How when we the charges, they come out of the positive terminal of the battery and they flow around all the way to the negative terminal of the battery. Okay. Electric current. Okay, we can define it with an equation. Okay. Our equation for electric current is I equals delta Q over delta T. Now, you already know that Q is charge, right? You already know that Q is charge. You already know that T is more than likely time, right? And that's what it is. So current is symbolized by I. This is the charge passing a point, okay? And this is the time it takes to pass that point. Okay. Okay. A couple of things, other things to note is that this can also be written a little bit differently. If you rearrange this equation, you actually get delta Q equals I delta T. And that's the same equation. It's just rewritten differently, right? Okay. The symbol for current, I already said, is I. Okay. And the units are what we call the ampere or amps. Okay. And we shorthand it with A. Okay. When you say that something has 7 amps, okay, 7 amps means that 7 coulombs of charge pass by each second. Okay. I just realized my face is so big in here, like you can hardly see like the notes. So let me do that. Okay. So 7 coulombs of charge pass by each second. That's when you say something has 7 amps. This means that 7 coulombs of charge are passing by. Battery storage capacity. We don't we don't really do too much with this, at least right now. Okay. But battery storage capacity is simply the amount of charge that passes through a battery before it dies, right? You know what, if a battery dies, right? It just doesn't work. This is the amount of charge that can pass through that battery before it dies, okay? You can determine the battery storage capacity from a current versus time graph, right? This is a current delivered by a battery shown as a function of time, okay? What is the storage capacity of the battery? So you notice that we have this graph of current versus time that is produced by a battery. It's steady, 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 steady here, right? Pretty steady there, and then it begins to decline until it hits zero. That's when the battery dies, when the current produced by the battery reaches zero, because now it can't, and now it doesn't work anymore. Well, to determine the amount of charge that's passed through the battery in the time of its life, we need to figure out, well, we could use the current times the time, or times the change in time. Well, this is our change in time. This is the current. We're basically going to find the area of this section. Okay? So if we find the area of this function, we can determine the battery storage capacity. Okay? So we have one leg that's worth 500 Okay, so it's 500 times 0.04. Okay, and you multiply that out, that gives you 20 coulombs. Okay, in this triangle, the leg is 500 and it goes and the height is 0.04. Okay, wait, we already did that, right? 500 times 0.04. There's one thing we're missing though, because it's a triangle. We need the 1/2 in front. So that's actually, we know that 500 times 0.04 is 20. So this is going to be 10 coulombs, right? Okay. So we can find it with the area of I versus T graph. Okay. And that gives us 30 coulombs of charge total, right? 20 pass by in the first section. It's dying, dying, dying. 10 more pass through. Okay. All right. Let's look through the next one. This next page is the last page of this section. It talks strictly about circuit diagrams, okay? Symbols that are in circuit diagrams, okay? This first symbol is the most basic and probably the most important that you're going to see. It's a wire, okay? If you see a straight line, that's a wire. Okay, this is a path for charges to flow through. Okay, it's like a canal or maybe a like a pipe or something, right? If you're thinking like water current, right? It's maybe like a pipe for it to flow through. This part right here, this thing right here is called a battery. Okay. Okay. You don't have to be this fancy about it, right? As long as it's got the long line and the short line, you can use just, that when I draw batteries, I just use the long line and the short line. Okay. Now, it's important to note that you can tell where the positive and negative terminals are on a battery like this. Okay. The long line is the positive terminal. The short line is the negative terminal. Okay. So there's that. You can tell where those terminals are. Okay. This is what gives charges energy as they pass through. Okay, it gives charges energy as they pass through. So when the charge passes through the battery, it gives it energy so it can keep going. Okay, this is the squiggly line here. This is a resistor. Okay, a resistor is any element that requires energy. As charges pass through. Okay, so if anything that plugs into the wall is technically a resistor because all of those things that plug into the walls require energy. Okay, this next thing is a special symbol for a light bulb. Okay, okay, you can either represent a light bulb as this or as a resistor. Okay, but this is a special resistor that converts electrical energy into light energy. Okay, so it converts electrical energy into light energy. Okay, this symbol right here is a switch. We typically draw switches open. Okay, we typically draw switches open so you can tell where they are. This is something that is used to control the flow of charges. Okay, if the switch is open, this is an open switch right here, right? Because it's detached, right? If it's open, okay, no current flows. Okay, if it's closed, current can flow freely. Okay. Okay. Next is an ammeter. Okay. An ammeter, it measures current. Okay. Ammeter measures current. Okay. Next is a voltmeter. Okay. A voltmeter measures voltage. Okay. And finally, this last one down here is called a capacitor. Okay. We don't really use capacitors in this unit. Okay. But you still need to be familiar with it. It can temporarily store energy by holding in opposite plates. I'm just going to shorten as op charges in separate plates by holding opposite charges in separate plates. Okay. We don't really look at capacitors very much right now, but it will become important later. Okay. That should be the first section just on electric current and voltage. All right. Have fun.